We will get started here as soon as I get the PowerPoint up. Yeah. Like that. So just some quick notes. Test 2, that is on Wednesday. Like before, you have all day to do it. So opens at 12 a.m. and closes at 11:59 p.m. Again, we'll be doing ProctorU. So make sure if you remove the browser extension, make sure you get it before you try and take the test. Now that you've done one test with ProctorU, hopefully, it will be good to go. As always, well, not as always, but even though you have until 11:59 p.m., I would advise against starting it past 11, just in case there's any like technical issues that might come up with ProctorU, like loading. We had some of that last time. It might take some time to resolve, unfortunate as it is. So just give yourself time in case anything like that happens. The best success I've seen people do this is if they take it in the afternoon or the morning. I've had zero problems with that. Seems people have more problems the later in the day they take it. My guess is that people take their tests at night, and everybody around the world is using this. So sometimes it might slow up, while during the middle of the day, it might be a little better. So I just suggest that. Make sure I put the announcement back on Blackboard, but just make sure to run through the test of your machine again and make sure everything's good to go. Does anyone have any questions? I can take a little bit of time this morning about questions about the test. Let me get the requisite questions out of the way. There's 11 questions. There are some questions with multiple parts. All the stuff that we will be tested over is in the test 2 folder of Blackboard. So make sure you go there. The test, I just went through the problems we did in the PowerPoints in the test 2 folder, and the questions come from the questions we did in class. If you have any questions about how to solve those, rewatch the videos for that lecture, email me, email our TA, we can get that all set up. You said the exam has 11 questions? I did. But some of those questions have part A, B, C, D, E, and all that good stuff. So 11 numbered questions doesn't mean there's only 11 questions, right? So by 11 questions, I mean 11 numbered questions. I didn't count up all the A, B, C, D, E, all that good stuff. You have an hour. I took the test this morning. It took me 5 minutes and 20 seconds. So hopefully that will be enough time for you to finish. So that's me going 12 times faster than the allowed time. So that's, that's generally where we want to be with these Gen Chem tests. How did I score? I got 100%. If I didn't get 100%, that would be something seriously bad with how I made the test, or my answer key is wrong. Any other questions? Oh, here's another question I always get. There's some multiple choice, some short answer, as in you try to solve the problems. I will be looking when I grade the problems, not only for the correct answer, but units. Make sure you don't forget the units, sig figs, all that good stuff. Anything at all. Partial credit. With the way that our tests are run, probably not, just because I won't be looking at people's work. So you either get it or you don't for those work problems. There might be some problems where you can get partial credit if you get the answer right, but that's just because the way because I have some questions like circle all of the right answers, where I give you right answers and wrong answers. So let's say you circled one right answer, then you get partial credit. But if you circle all the right answers and then like all the wrong answers, then you get no credit. A sinister laugh. I mean, I'm not evil. I'm trying to help you. I'll do my sinister laugh on Wednesday when it's 10 a.m. and I don't have to teach a class, and I'll be sipping here with my coffee and saying, yes, yes, my pretties. I want everyone to do well. So people want to tour and will they'll still get extra credit? Yes. I'll be getting that list. That opportunity is still good until Wednesday. I think there is a session on Wednesday. So if you want to go to that, you'll still get credit. Yeah, you'll get extra credit put on your test. If you've gone to our TA, our tutoring sessions from the time of test 1 to now. Anything else? Oh, the equation sheet's online. Make sure you print that out. All that good stuff. If you have questions about the equation sheet, feel free to ask. Sometimes I'm confused using the correct R. Don't worry about that. That's on test 3. So you shouldn't have to use the gas constant on test 2. It's the only difference with the two we've used in class is the pressure being measured in atmosphere and pressure, or pascals. So we haven't used pascals as a pressure unit. It's either torr or atmosphere. But yeah, the only difference between any gas constant, any R you'll see, is the units it's in. That's it. So when we look at the problem, just see what units we're in and look at the gas constant and make sure they match up. You get extra credit for attending SI sessions from test 1 up to this Wednesday? You sure do. Just a bonus for going there to learn. I think I announced that like when we were going over test 1. I don't know. I announced that a while ago. I don't quite remember. It's been a wild semester. Can you believe we're like almost halfway done? Time goes so slow and so fast at the same time. All right. Well, if you do have any other questions, feel free to type them in. Otherwise, we will get started. This material is not on test 2, so you don't have to worry. This material will be coming at you in test 3, though. So this is test 3 material. All right. Okay. So what are we talking about today? We are continuing our discussion on the gas law, the ideal gas law. And we first are going to talk about the idea of partial pressure. Now, when we're working with ideal gases and we have a mixture of gases, the pressure that we measure is just the combination of the individual pressures of each of those gases. So what I mean by that, imagine that you have a mixture, right? You just have a sample of gas, and in that gas you have N2, O2, argon, and carbon dioxide, right? The total pressure from those gases, the total pressure that we measure is just the sum of all of the individual pressures. And that's what we're doing here. So what we're doing is we're taking the ideal gas law, PV equals nRT, and we're solving for pressure. So we're taking each side and just dividing by V. So it's written out a little weird where it's N times a parentheses RT divided by V. But what that's really saying is that, if we have a mixture of gases, R's the same, T's the same, V's the same. And so pressure is really just dependent on how many moles of a substance you have. But to calculate partial pressure for each molecule, it's just moles of N, RTV, O2, moles of O2, RTV, so on and so forth. And then we can calculate the total pressure by simply adding up all the partial pressures, right? Now, another idea that goes along with this is mole fraction. So mole fraction is if we have this combination of gas, I want to know like what percentage of the moles are made out N2 or what percentage of the moles are made out O2. And that's a rather simple concept, right? So if I want the mole fraction, and the symbol for that is this weird looking X. If I have my Greek symbols right, I think that's chi. It's a Greek letter. You can call it X if you want. Doesn't matter to me, but that is the Greek, I believe, chi. What you do is you take the amount of moles of N2 divided by the total moles of all your gases, and that's mole fraction. So that's a rather simple concept, at least mole fraction. So we're going to start today, see if we understand these concepts, this concept of partial pressure. So let's say I have a gas mixture. It is one, and the total volume. So the total volume of my mixture is 1.35 liters. My temperature is 25 C. You see here, I'm writing letters above it because anytime you see like gas, most of the time you're going to do PV equals nRT. So it's a good practice to just write out which numbers go to which variables when we start, right? So at 25 C, in each of the following gases at the partial pressure, so pressure, and pressure. So we have three gases, three different pressures, and we have three questions, A, B, and C. A, what's the total pressure of my mixture? B, what is the mole fraction of each gas? C, what is the mass of each gas? So that's where we're going to start. So I'm going to give everybody a couple minutes and see if we can work through that while I recalculate B, because I just realized rereading it, I did B slightly wrong in my answer sheet. So yeah, try to do that. So hopefully A is relatively simple, right? What's the total pressure? Just add them up. It is 434 torr. If you want to convert that to atmosphere and add it up, that's fine. I just left it as 434 torr. That's total pressure. B might be a little more difficult. It's going to take some thinking of how do we get moles using our gas constant. So let me just do nitrogen for B, at least part of it, all right? So N2. We know N2 is 215 torr of pressure. If we're trying to solve for moles, we have to go back to our ideal gas law, where N is the number of moles. So we have a pressure for nitrogen. We have a volume for nitrogen. Here's volume. We have a temperature for nitrogen. There's temp. We have a gas constant. So all we have left is number of moles. So one equation, one variable missing. Perfect. Our gas constant is in atmospheres. Our pressure is in torr. So we need to convert N2, the pressure, from torrs to atmospheres. All right, so there are 760 torr in 1 atmosphere. Torr cancel out, we're left with atmosphere. So when we do that, that is 0.283 atmosphere. Now we have everything we need. PV equals nRT. I'm solving for N, so you divide each side of the equation by RT. You get N equals PV divided by RT. I always put my unknown variable on the left, so that's what I did there. If you want to keep it on the right, that's fine. So N equals at pressure 0.283, volume 1.35, R 0.08206, T. Now T's in Kelvin. Here we have it in Celsius, so we need to convert. 273 plus 25 equals 298 Kelvin. That's room temperature. And the number of moles of N2, when we do that, are, so N2, 0.0156 moles, right? So that's the first step in B. You need to tell me, well, I should give myself more space, but you need to tell me how many moles of O2 do we have, right? How many moles of helium do we have? And then to get mole fraction, it is just total moles. And for N2, it would be moles of N2 divided by total moles of gas, right? So see if you can figure out now, in case you were a little lost there, I did N2 for you. See if you can follow that logic for O2 and helium now. All right, so for O2 and helium, I'm not gonna like work out the exactly how you do it because I have the N2 example there. But just to move things along, I'm gonna write down what the answers I got were. So O2 has a pressure of 0.134 atmospheres when we convert it. And when we do PV equals nRT, that should be 0.00740 moles. And helium, when we convert it, helium has a pressure of 0.154 atmospheres. So when we convert helium into moles, we got 0.00850 moles. So before I move on to actual mole fractions, are there any questions about how I solved for the amount of moles of each individual gas? As that is something we went through on Friday using PV equals nRT. Now we're doing for multiple gases. But if you have questions about how I did that still, please let me know. How did you get the temperature for N2? Because it's in the question. I have a gas mixture in a 1.35 liter sample at 25C. That means all the gases are 25C. And if we look at the gas constant, we want a temperature in K. And in fact, for science, you like almost always use Kelvin because the negative temperatures of Celsius make calculations not make sense. So I converted it to Kelvin by taking my Celsius and adding 273. And so that's my temperature for nitrogen. It's also my temperature for oxygen and helium. Any other questions? Okay, so next we have to do mole fraction. So we have to do total moles, and it's just simply adding up the moles of nitrogen, oxygen, helium. So 0.00156 moles of nitrogen plus 0.00740 moles of oxygen. So there's nitrogen, there's oxygen, plus 0.0085 moles of helium. The total amount of moles that I have of this gas mixture are then, whoops, undo that, there it is, 0.0315 moles. Then to do the mole fraction, you just take each individual gas, so 0.0156 divided by total moles. So you would see that for nitrogen, the fraction of our total gas that's made out of nitrogen is 0.495 or 49.5%. I'm just going to leave them in decimals, but it's 0.495. Oxygen is 0.235, and helium is 0.270. And a good way to check that you did this right is that all your mole fractions should add up to 1, which they do here. How do you get the amount of moles again? PV equals nRT, right? Where did I do that? PV equals nRT. Yeah, right here. So nitrogen. I give you a pressure. I give you a volume, give you a temperature, just solving for N for each individual gas. See what mass of gas is present. This is actually review from earlier in the semester, but it's always good to go over. How do I convert moles to grams? I need molar mass. So you need to look up in your periodic table molar mass for N2, O2, and helium. And so I'll do N2 here. So N2, I have 0.0156 moles of gas. Periodic table, Nitrogen has a weight of 14 grams per mole. So N2 would be 28. So the molar mass of N2 is roughly 28 grams per mole. There are decimals there. I was just too lazy to do that. So I just left it as 28. On the test, you should use the decimals, but here I'm just going to say 28. So I want to convert this into a weight. So for every 1 mole, and I know mole goes on the bottom because I start with mole here at the top, so moles cancel out. 1 mole is 28 grams. And so when solving that, the weight of nitrogen I have is 0.437 grams of N2. And then we do the same thing for oxygen. We do the same thing for helium. So I'll just do those really quick. O2, 0.00740 mole. Look at periodic table. 1 mole is 32 grams. That's 0.237 grams of O2. Helium, what you should get for helium's really light. That's 0.0340 grams of helium. So that problem is a bit long. It's using a lot of the skills that we've learned not only on Friday, but also throughout the semester. But really, it's just the ideal gas law. Solve for number of moles using PV equals nRT. And then once we have moles, we can go to grams using molecular weight. So looking at all of that, are there any questions about anything I did or any confusions about what I did and why? If you have those questions, now is your time to ask. How do I go from atmospheres to moles? PV equals nRT, right? Atmosphere is the pressure. I have a volume that's given in the problem, 1.35. I have a temperature, which is 25 C. So when you solve for PV equals nRT, you just have NB by itself, or N's number of moles. So that's how you convert between a pressure and number of moles. So here's the work for N2. I have 0.283 atmospheres. My volume is 1.35. R is given. Temperature is 298. So whenever you're working with a gas and you're given a pressure and you're asked to calculate number of moles, PV equals nRT. So any gas that has to do with either pressure, volume, moles, or temperature, the equation you're going to use is PV equals nRT. PV equals nRT is your friend. We use that for like gases all the time. The ideal gas law. Right. So if there's no other questions, we will move on to our next concept. So I will clear all this doodling, and we will move on. The next thing we're going to talk about is the idea of collecting gas over water. Okay, so water or any liquid will always produce a gas above it. And the gas and the liquid are in equilibrium. For water, we call the pressure of the gas vapor pressure, right? So if you ever look on like weather and it's talking about vapor pressure, and they'll report vapor pressure in torr, right? The vapor pressure is like 23 torr. What that is saying is that is how much gaseous water, or steam really, how much steam is in the atmosphere. And this really is dependent on temperature. the higher the temperature, the higher the vapor pressure. When you get to the boiling point, vapor pressure is basically the same pressure as the atmosphere, more or less, right? And this is also why liquids will dissolve, or not dissolve, why liquids will evaporate below the boiling temperature. So if you leave like a glass of water on your desk and you come back 2 weeks later, that water will be more or less probably gone, or a lot of it will be gone. And that's because water is constantly turning into a gas, even below the boiling point. If we take this water and we enclose it, though, if we have like an enclosure here, then we're going to reach a state called equilibrium, where the amount of vapor in there will be a constant, right? And so we know what the vapor pressure is at any given temperature, right? So any temperature, we know how much gaseous water should be in an enclosed container system, like I'm showing here. Now, why is this useful for us? So a common laboratory technique to collect gas is that what you do is you take the gas and you just funnel it through water and it will bubble out into this container. So let's say we want to collect hydrogen gas. One way you can collect hydrogen gas is if you take zinc and you dissolve it in hydrochloric acid, right? And what will happen is that hydrogen gas will flow out into the water and then it will flow into this container, right? So collecting gas over water is a very common chemistry technique. Now, inside this container, you have two different gases. You have hydrogen gas and you have H2O gas, right? And so the total pressure that you measure in this container is due to your two different gases. So if you want to know how much hydrogen gas you have to know the vapor pressure. Then you measure total pressure. So if I have the total pressure of my mixture, my total pressure is equal to the partial pressure of hydrogen gas plus the vapor pressure of water, or the partial pressure from water. And like I said, vapor pressure is temperature dependent, increases with temperature. So let's see how we can actually use this concept in a real life situation. So let's say I have a copper plated penny, and inside, if you didn't know, the inside of a penny is zinc. And if you also didn't know, it costs like 2.5 cents or something like that to create every penny. So every time the US Mint makes a penny, it actually costs 2.5 pennies to make. All I'm saying is we should get rid of the penny. Who carries around pennies? Anyways, so let's say I take a copper plated penny and I put that in hydrochloric acid, right? And what will happen is that the hydrochloric acid will react with the zinc inside the penny. And the reaction is given here, or we have two acidic hydrogens plus our solid zinc will make hydrogen gas, and the zinc will dissolve. It will become aqueous, right? And let's say that when I'm dissolving this penny, I'm collecting the gas over water, right? And so I'm collecting this gas and my temperature is 25 C. And the amount of gas total that I collect is 0.951 liters. And the total pressure of all my gases combined, my total pressure is 748 torr. With all that information, I want you to tell me how much hydrogen gas we actually collected if the partial pressure of water at 25 C, which is the temperature we're at, the vapor pressure of water is 23.78 torr. So see if you can combine all that information. And for these word problems, there's a lot of stuff in here we don't actually need. So I try to highlight what the important stuff is, right? So see if you can use the problem we did beforehand, question 1, and synthesize it with this new information to tell us what is the pressure of hydrogen gas. So I have a question. There was a question on the reading guide that we had to use a chart of pressure based on the temperature. Are we going to have to know that chart? I will never ask you to memorize a chart. If there's any chart we need for a test, I will teach you how to read it during one of our lectures and expect you to know how to read it, but I'll never ask you to memorize a chart. So we will probably not use that chart on the test as we are not using it right now. See if you can solve how much H2 did I collect if my total pressure is 748 and the pressure from water is 23.78. So I'm gonna give everybody a couple minutes to struggle through this. So if you feel like you're struggling, here's some of the questions you should be asking yourself, right? Okay. I need to know mass of hydrogen gas. That's what I'm trying to get at here. What is the mass of hydrogen gas? And I'm using, and it's a gas, so I'm using PV equals nRT. That's the ideal gas law. When we're using a gas, we're going to be using that equation the majority of the time. To get to mass from any of these constants, the variable we need to solve for is n. N equals number of moles, right? So what you should be trying to solve for is n, where n equals RT divided by PV, right? So if I go back to my problem, I see my temperature is 25 C. Well, if you look at the gas constant, it needs to be in Kelvin. So let's add 273 to that. My volume is 0.951 liters. That matches up to the volume in the R constant. So that's good. My pressure, okay. Well, in the problem, I have a total pressure. So my flask has both H2 and H2O gas in it. And in total, the pressure is 748 torr. I know the pressure of water at 25 C, so H2O, is 23.78 torr. So now I have to figure out the pressure of hydrogen. Well, P total equals pressure of hydrogen gas plus pressure of H2O, right? Based on what we did in question 1. So solving for the pressure of hydrogen gas, we get that hydrogen gas is 724.22 torr. All right, before I move on to the next step of the problem, based on what I did there, are there any questions on how I solved that? Or questions about how that was done, my logic? I'm trying to be super explicit here, showing my logic for solving these more difficult problems to just show you how I work through them. All right, what questions am I asking myself? How do I actually set these up on a piece of paper when doing these? All right, so I have my pressure of hydrogen gas. So I do have a pressure, which is 724.22 torr. If we look at our gas constant, though, we see the gas constant's in atmospheres. So I don't want to be in torr. I want to be in atmosphere. So I need to convert it. So 724.22 torr. For every 760 torr, there's 1 atmosphere. So I'm doing that conversion, and that is 0.95292 atmospheres. Now I have everything I need to solve for N. I have a gas constant, I have a temperature, as long as it's in Kelvin. I have a volume, and I also have a pressure in atmospheres. So let's solve for N now, putting in all those variables. And when we do that, we find the number of moles of hydrogen gas equals 0.0371 moles. All right, that's how much hydrogen gas we have. And we can directly calculate that from pressure. So whenever you have a gas, if you have a pressure and a volume and a temperature, you can figure out how many moles that is. And from moles, as we learned early on in this course, we can calculate grams. So the molecular weight of H2, we can find that in the periodic table, is 2.016 grams per mole. We're in moles, so we want to go to grams. So every 1 mole, moles cancel out because I have 1 on the top, 1 on the bottom, is 2.016 grams. I'm left in a weight of grams. So if I do that calculation, the amount of hydrogen gas that I created was 0.0747 grams of H2. Again, these I understand these problems are more difficult than what we were doing on Friday, just using straight up PV equals nRT. But this kind of shows you all the applications we can do with the ideal gas law. And hopefully by working through something like this, I can show you like the thought process that I go through when trying to solve more complicated problems. Just, try to get rid of all the stuff that doesn't matter, right? So when the zinc in the niche, that's actually all nonsense. I only care about the equation. Write down my variables, actually label my numerical numbers to try and put them up with variables, right? So T, V, P total, vapor pressure. Write my equation down, match those up to the variables I have and then variables I don't have, and try to figure out a way to solve for the variable I don't have. So here it was just, well, I know my total pressure. My total pressure is the pressure of hydrogen and water. I have my pressure of water, so then I have my total pressure, so all I need is that hydrogen. And from there, solve for N. From there, go to grams. So are there any questions on how I solved that problem? Logic, steps, anything at all? Now we're doing chemistry. Now we're finally getting into some real chemistry. I mean, I guess this isn't really chemistry. This is just measuring pressures, but it's close. We're close to doing real chemistry here. This is an application of chemistry. All right, well, if there's no questions, well, there is. I keep getting 26 moles. 26 is going to be huge. So let me just do the calculation. If you're getting 26, make sure you're using the atmospheres, not the torr. You might be getting 26 if you're putting in 724 torr. I could see like 26 for that. Let me just do it really quick here. So R, and it should be a small amount because the pressure is not that huge. So R is 0.08206 times temperature, which is 298, divided by pressure, which is 0.95. Did I do something wrong? Let me see here. 0.95292. Oh, I know what I gave you the wrong. I don't know how to do. Yeah, my bad. I did the wrong division. It should be N equals PV divided by RT. That's why you're getting 26. So if you do 1 divided by that number, you'll get the right number. I just, I divided wrong in my head. I don't know how to do math, apparently. Mea culpa. Sumimasen, wakarimasen, algebra, shite, ikimasen. That is not correct Japanese. Anyways, that's basically all the time we have. It is 10:50. So if you do have questions, please let me know. Please let the TA know. I'll put a homework up. Remember, there'll only be 2 parts. Test is on Wednesday. This will not be on the test. But good luck on the test. Make sure you test your system before Wednesday. Do not try to start the test at 11:30. You might run into problems, 11:30 p.m. Otherwise, I'm here to help you. RTA is here to help you. Please let us know if you have problems. And good luck on Wednesday. I hope everybody does well. I do not like it when people, it is not my intention for you to do bad. I'm rooting for everybody. All right. Take care, everybody.